Hello everyone. So this again is one of the most important topic of this chapter, magnetic effects of current. So what is this law? Ampere circuital law. Ampere circuital this law states that line integral of magnetic field about a closed path. Now we have to talk about line integral and a closed path. For that, consider this plane of paper. Okay, I have taken this plain sheet of paper like this, and from here I am crossing a wire like this. So this is my wire carrying current I passing through this plain sheet of paper. Alright. So I have to find line integral of magnetic field about a closed path. For that, the magnetic field, what is the direction of magnetic field? According to right hand thumb rule, it will be like this. Okay, the circular path. Line integral of magnetic field about a closed loop or path or circuit. Everything is applicable according to law. Line integral of this part. What is line integral, by the way? I have taken this name 4 or 5 times in last 1 minute. Line integral, surface integral and area integral. There are different types of integrations. When you have to integrate something with respect to length, then it is line integral. With respect to area, it is surface integral. With respect to volume, it is volume integral. So here the integration sign, line integral of magnetic field, that means B. Line integral means it has to be integrated with respect to length. So B dot dl, line integral of magnetic field about a closed path, is equal to mu naught times total current threading the path. Mu naught times total current threading the path. This is the statement of Ampere circuital law. So how we are going to prove it? Let's start. We'll start from this point, B dot dl. What is B dot dl? First of all, before even integrating, you are going to remove the dot sign. That is, you just elaborate the dot product thing, which is B dl cos of theta. So what is this theta between? This angle theta is between B and dl, right? Where is B? This black circle itself is the magnetic field about this wire, and dl is a small part on this magnetic field dl. So we are doing the line integral of magnetic field itself. So that is why the angle between B and dl, they both are in same direction. So it is 0 degree. You are left with B dl. B dl, that means magnetic field B, which is a constant, into dl. dl, integration of dl is going to give you the complete path, which is what? If this radius is r, that dl integration is going to give you 2 pi r, which is the complete length. So here we have B into 2 pi r. Now we have already done this in what? Biot Savart law. What is the magnetic field due to straight current carrying wire? Magnetic field B, the formula for magnetic field was mu naught I upon 2 pi r. Which case was this? This is the case of infinite length. So taking this value, putting this value here, we have from this equation B dot dl is equal to B into 2 pi r, which is mu naught I into 2 pi r multiplied by what? 2 pi r. So you get mu naught I. Hence the statement of Ampere circuital law, which states line integral of magnetic field about a closed path is equal to mu naught times total current threading the path. Now, since this Ampere circuital law is valid for many applications, let's do 2 important applications, that is to find magnetic field due to a solenoid and magnetic field due to a toroid. Okay, what is solenoid and toroid? Toroid is a circular solenoid, and what is a solenoid? I'll tell you. Solenoid structure is like this. You guys have seen the spring. So consider one part of the spring taken out, another part, the extreme ends are taken out. Current is given from one side and the current is going round and round and coming out from the other side. That is what a solenoid is. This is a solenoid. The dotted lines, consider consider these dotted lines to be those part of the solenoid which is on the back side of the spring, and this is on the front side of the spring. So this is how a solenoid is. We want to find out the magnetic field which is inside this solenoid. It will be like this. Okay. How do I know it's going to be like this? I might have drawn the wrong direction of magnetic field. Magnetic field might be in this direction from right to left. How do I know that? See, current, what is this? Look at the direction of current in any case. For example, this is your wire or a metal rod, and you have one wire like this. So if current is going in this direction, you just have to use the right hand thumb rule and locate the direction of current. If current is in this direction, that means magnetic field is in the direction. If current is in this direction, magnetic field is in this direction. Okay. So similarly, here our direction of current is like this. In each thread, it is coming like this. Basically, in our syllabus, this particular topic, there is sometimes students usually don't get this diagram. You can also in many books you must have also seen the diagram like this, like a round and a dot and a round and a cross. What they actually mean by this diagram is the wire is coming out from these dot parts and the wire is going inside these cross parts. So it is easy in that way to explain which part of the wire is coming out from where. Okay. So according to this, you can easily figure out that current is coming in this direction. So using right hand thumb rule, magnetic field is in this direction. I want to find out the value of magnetic field inside this solenoid, and I'll do it using Ampere circuital. How? See, first of all, I'm going to take an imaginary rectangular loop inside and outside this solenoid, because according to Ampere circuital law, line integral of magnetic field about a closed path. So I have to make any closed path, right? So this is my closed path, the rectangular path. Line, and I'll do the simple line integration about this path, and I'll find the value of magnetic field. That's a very simple application. So for using this application, also keep in mind, first find the value of exactly the way we did it in Gauss theorem in electrostats. First find out the value of line integration by yourself. Whatever the answer is, use that answer and equate it with the formula that B dot dl was equal to mu naught I, and you will get your desired result. Line integral of magnetic field about, I have a very bad handwriting, so keep on listening what I am saying. Line integral of magnetic field about the closed loop. Let's name this loop A, B, C and D. Okay, about this closed loop A, B, C, D will be line integral B dot dl of A, B, C, D. Whatever the answer, whatever the outcome of this expression will be, I'll be using that straight away and I'll be equating it with mu naught I. That is what Ampere circuital law has already given to us. So this is, I can bifurcate this whole integration into 4 parts, which is B dot dl from A to B for this length, then B dot dl for BC, then B dot dl for CD, and finally B dot dl for DA, right? Now we'll find out the value of each part separately, starting from what is B dot dl for A to B. Direction of magnetic field is in this direction, and length after integration of this B dot dl, the length would be from A to B, that is AB length. But no matter what, this AB is perpendicular to the magnetic field lines, that means theta is equal to 90 degree. So here, if you expand it in the terms of dot product, it will be B dl cos 90, that is for AB part, then B dl cos, what is for BC? For B to C, B and C, BC and the magnetic field, both are in same direction, that means 0 degree plus B dl cos 90 for CD part, and lastly 0. No B dot dl even for AD, because there is no magnetic field present at AD part. So for that I have taken straight away 0. this thing, due to this cos 90, this is going to be 0, this cos 90 is going to be 0, we already have an 0, so all we are left with is this b dl cos 0 for the length b to c, which will be, okay, let's take this length equal to L. This is the small length L and the total length of solenoid be capital L. Alright, so my answer here would be b dl for b to c, which is equal to b I have taken out as a constant, integration dl for b to c, which is equal to the total length of bc, which is small l. So I am left with this answer, which is bl. So this whole thing ABCD will be equal to BL. Okay, now please note it down before I rub it. Pause the video, note it down, and the final result was B into L. I am putting this result here. According to Ampere's circuital law, what was, now you can write it this way. According to Ampere's circuital, don't use these kind of abbreviations, it's not allowed in your board exams. Ampere's circuital law, I am writing it because of lack of space. B dot dl was equal to mu naught times, I can straight away write I here, but I am going to write mu naught I times total current threading the path. What is the total current threading the path? Total current threading this path is current through each loop into number of loops which are in this length L. Right now, according to this diagram which I have made, just 1 and 2, there are 2 loops which are crossing this length B to C, not this loop and not that loop. Getting my point? So that is why here this is mu naught into current through each loop. Write exactly like this, current through each loop into, or current through each turn, that will also be correct, into total number of turns. Alright, so this marker is dead, so this is mu naught into I into total number of turns. How would I know? In this diagram it is very clear, I can actually count that there are just 2 number of turns within this length, but in reality the solenoids are like this much close. So how are you going to count the number of loops from this length to this loop, this length, like this much length? For that we have another term. Number 1 we have complete length, and number 2 we have total number of turns which is in the solenoid, which manufacturing companies actually they give this thing, this figure, that this loop has this much number of turns. So we have another quantity which is, or property, small n, which is what? Total number of turns per unit length. Total number of turns per unit length or upon total length. This is how we find small n. So small n is basically, this small n is total number of turns upon total length, right? So how can, suppose, consider this example, suppose we have 50 turns, okay, and I have this length to be 5 centimeter. Can you calculate how many number of turns are falling in every 1 centimeter? What will you do? You divide 50 by 5, right? So 50 upon 5 gives you 10 turns. So there are 10 number of turns in every centimeter, 10, 10, 10, 10 and last 10. So we will get 50 number of turns. So using this fact, in 1 centimeter there are 10 turns. That means if I have a length of this much, which is 2.8 centimeter, so I can easily do 2.8 into this thing. Each centimeter has 10 turns. That means 2.8 centimeter will be having 2.8 into 10, which is 28 turns or 28 loops. Similarly, I have to find the total number of turns falling in this length small l. So that will be, total number of turns is what? L into small n. Total number of turns per unit length into this length L, right? Okay, so this was our one of the result. This is our another result according to Ampere's circuital law, and both are from the same derived fact. So equating or from equation 1, I'll rub these things, it will confuse you. From equation 1 and equation 2, what do we get? B into L is equal to mu naught I L N. L goes cancel out, so we have B is equal to mu naught small n I. This is the formula for magnetic field inside a solenoid.